Okay, so now that we know how to graph a single linear inequality, let's talk about graphing a system of linear inequalities. We'll start with a simple system. If you have a system of two linear inequalities like this, what you want to do is find where the two inequalities overlap. Now, this is not necessarily how I would do this problem, but I'm going to do it in three phases here just so I can be sure and show you. So I'm going to graph the first inequality, 2x plus 3y is greater than 12. And we already know how to do that. You just find the boundary, which is 2x plus 3y is equal to 12. Let x be 0, solve for y to get your y-intercept. Let y be 0, solve for x to get your x-intercept. So it goes through 0, 4, which is right here, and it goes through 6, 0. And then, since it doesn't have the equal to, I draw a dotted or a broken line to connect them. And then when I plug 0, 0 in to test, I'll get 2 times 0 plus 3 times 0 is greater than 12. So it'll just say 0 is greater than 12, which is false. Okay, so that's false. So that means I have to shade the opposite side. So you can see I shaded the region above the line. And so that's for that inequality. Now for the second inequality, 2x minus y is less than or equal to 2, the boundary would be 2x minus y equal to. So let x be 0 and solve for y, and I get negative 2. Let y be 0 and solve for x, and I get 1. So it goes through 0, negative 2, and it goes through 1, 0. And then I'm using a solid line this time because I do have the equal to with this one. Now I want to know where these two overlap. So if I put them on this, I'm sorry, I didn't tell you about the shading. If I test 0, 0 here, which is above the line on this example, if I plug 0, 0 in, I get 0 is less than or equal to 2. Should technically have a less than there. That's a true statement, so I shade everything on the same side as 0, 0. So I shade, this side. And now when I put these two together, everything above this line and everything above this line, when I put them together, it's going to give me this region here that's bounded by this broken line here, and then bounded by a solid line here. And so it's going to give me the region, this region in here. And of course it's unbounded because it goes on forever and ever. But that's an unbounded region. Now, this region has what we call a corner point. It only has one corner point because it's unbounded and goes on forever and ever out there. But right here where the two lines intersect, we call that a corner point. And to actually find the corner point, what you would have to do is you would have to actually find where the two lines intersect by solving this system of equations. And you could just use a calculator and do RREF if you wanted to. Put that in an augmented matrix form and solve it, and you would get 9/4 and 5/2, which in decimal is 2.25 and 2.5. So anyway, that's how you solve a simple system. Here's another one. 2x plus y is less than or equal to 8. 2x plus y is less than or equal to 10. X plus 2y is less than or equal to 8. So by now we've probably mastered graphing single inequalities, so let me just kind of brush through this. Your intercepts for the first boundary are 0, 10, and 5, 0. So I plot 0, 10, and 5, 0. And again, you can do all these on the same graph. I'm just doing it this way so you can see it better. And now this has the equal to, so I do a solid boundary, so I draw a solid line. And then I test 0, 0. And when I plugged 0, 0 into the first inequality, I got a true statement. So I'm going to shade the same side as 0, 0. So you can see I shaded the region below the line. Okay, and now on the other line, its intercepts x plus 2y equal 8, its intercepts are 0, 4, and 8, 0. Well, 0, 4 is right here, 8, 0 is right here. And so again, I have the equal to, so I draw a solid line through there. And then I test 0, 0. And when I plug 0, 0 into this one, I got 0 is less than or equal to 8, which is again a true statement. So I shade everything on the same side of 0 as 0, 0 is. So I shade that side. And now when I put these two together, if I lay these two regions on top of one another, they're actually going to intersect in this region. So let me find my cursor here. Where does it go? All right. So it's actually going to intersect out here in this region. And let me show you where the two, it's bounded by this graph here, and then it's bounded by this graph here. So it changes direction there, and so that represents, so it shows you it's bounded here by here. So this dark green region is actually the overlap. So you need to emphasize that more, show the overlap. Now again, it has what we call a corner point right here. The corner point is really just a vertex. It has a corner point right here of 4, 2. And again, to find that corner point, you simply solve the system that makes up that point, which would be these two, solving this system of equations, and you would get that point 4, 2, which is the corner point. Okay, now corner point is basically when you have a region, you know, it's basically the vertices of the region. So right here you actually have 5 corner points. So for this region right here, 0, 0 is a vertex, 0, 10 is a vertex, 5, 8 is a vertex, 9, 4 is a vertex, and 11, 0 is a vertex. So these are called corner points. Okay, and so these corner points are important for us as we get into linear programming. Okay, let's do a more complicated problem. Now I have 3 inequalities. Now notice I'm using x1 and x2 instead of x and y. So 2x1 plus 4x2 is less than or equal to 24. So let's see if I graph that. The boundary would be 2x1 plus 4x2 equals 24. So if I let x1 be 0, x2 is 6. If I let x2 be 0, x1 is 12. So this goes through 0, 6, and 12, 0. And I have a solid line. And then if I plug 0, 0 in, I'll get a true statement. So I shade everything below the line. Okay. Now over here, I'm going to do the second one on top of this. Here's this pink one here is the first one. Okay. I don't know if you can see that very well, but here's the one I just did right here. Okay. And then, okay, and so now I want to graph this other one. So I have this other one, the second one I'm going to graph is 3x1 plus 3x2 is less than or equal to 21. And its boundary would be 3x1 plus 3x2 equal to 21. So if I let x1 be 0, x2 is 7. Let x2 be 0, x1 is 7. And so it's going to go through 0, 7, which is right here, and 7, 0, which is right here. And then you'll see that I drew a solid line here to connect them. And then when I test 0, 0 for that one, I get a true statement. So I have to shade everything below that line, because 0, 0 is below it, and I got a true statement. But notice that this dark green area is actually where these two overlap. So let me just kind of move that out of the way. So really the overlap here is is bounded here and then bounded, let's see if I can draw this through here, bounded there. And so it's everything below these two lines. This region out in here is the region. So, but I still have a third one to bring into the picture, and this is 4x1 plus 2x2 is greater than or equal to 20. So the boundary would be 4x1 plus 2x2 equals 20. And if x1 is 0, x2 is 10. And if x2 is 0, x1 would be 5. So that goes through 0, 10, and 5, 0. And then again I draw a solid line. And notice when I test 0, 0 for this one, since it's a greater than here, it's going to do something different. I'm actually going to get a false statement, because I'll get a false statement. So that means I got to shade everything on the other side of the line. So that would be, you know, this region out here. And so then I shade that region. Now if I were to be able to pick this up and just slide it over to here, you would see this purple region would come on along in here. And let me just show you here. This would come in here like right there. And then, so basically what it does is I had this dark green region here, but what that does is that basically cuts out all of this stuff over here and just gives me the stuff that's bounded by, I'll show you these two lines. Let me show you the boundary. It's bounded here by this piece, and it's bounded here. Let's see. I'll get it right in a minute. Okay, so it's bounded there. Come on, spin for me. Okay. Just give me a second here. Okay, so anyway, if you can see these two red lines, it's everything between these two red lines, but notice it continues on and on forever. So it's that dark purple region that goes on down and down and down is the region. And so that's the final solution there. On this example, I don't really want to bring anything new here. I just want to show you that you graph this portion of it just like we did before with the other examples. You know, you're going to find where the intercepts are. You're going to draw the boundary, and then you're going to shade, and then you're going to do the next one. You know, this one's actually going to go through 0, 13 and 13, 0, and then you're going to shade below. So that dark green region would be the region we have so far. And then when you bring in this third inequality, it goes through 0, 10, and 25, 0. So that brings in this purple region here, right here to here, and then you shade everything below that. But basically what that gives us is we're bounded here, and then here it turns, and then here it turns again. So we've got everything below those boundaries here, all of that stuff in here. But what we've also got, which you might not have noticed, is x and y must be greater than or equal to 0. So that means we have to restrict ourselves to the first quadrant. So if we restrict ourselves to the first quadrant, you can see here I drew the little red lines to show you the boundary. And what you have to do is, you look at these vertices, you have 0, 10, 5, 8, 9, 4, 11, 0, and 0, 0. Now 3 of these came from just knowing where the x and y intercepts are, but these other 2 actually had to come from solving the system of equations that made up these points. So each of these points came from a pair of equations, and so you had to solve that system. So I'll finish this on another video, but basically this is where we're headed right here, to restrict ourselves to the first quadrant and find the region associated with that.